So what I'd like to do today then is go ahead and jump into Chapter 7. So Chapter 7 deals with transient analysis of circuits with inductive and capacitive components. And so this is really the one aspect of circuit analysis that we haven't touched upon yet, because we have talked about steady state DC, we've talked about steady state AC, but it's always been steady state. So let's jump into this material here. So in this chapter, we will be discussing transient analysis for first order and second order circuits. First order will refer to circuits that have one energy storage element, so one inductor or one capacitor. And what we want to know is how the circuit responds to a sudden change in configuration or input. That disturbance could be something physical, like a switch being flipped. It could be an additional source being turned on. It could be a short being applied. So a purely resistive network would react instantly. Right? There's no relevant transient response for a purely resistive network. But for a network with inductive and capacitive elements, or elements that act like inductors and capacitors, we do see a transient response. So one important value is the circuit's time constant, which is represented by the value tau. And so this time constant tells us how long it will take for the transient response to settle. And this is important to understand, right? Because let's say you're dealing with a switching circuit or something in the realm of digital, okay? Where we have a processor or some sort of digital element that's switching between 0 and 1, and you want to know how long after the switch do you have to wait before you can store that information into memory, or how long after the switch do you have to wait until you can perform the next calculation, right? Because you don't want to start that calculation while the transient is ongoing. You might accidentally get a 0 where there should be a 1, or get a 1 where there should be a 0. So transient analysis is important for learning about the transients themselves, but it's also important for steady state problems, or more, let's say, robust design problems. So one example we see, and this is from the text, is this circuit that is supposed to represent the flash for a camera. And so what we have is some voltage source with an internal resistance, and when the switch is in the green position, we charge the capacitor. And the right-hand side of the circuit is disconnected. So it's either green or purple, not both. Then, when we want to make the flash actually flash, what we do is we flip the switch from green to purple, and the capacitor at this point should have a voltage across it and have a significant amount of charge stored within it, and that charge will be discharged across the resistor R bulb. So we have state 1 and state 2. I've numbered them kind of counterintuitively, but purple, then green. So what does this look like? We're going to introduce first the solution to a problem like this, and then we're going to go back and talk about how we actually get that solution. So for those of you, well, everyone in this room should have taken or be taken ENG212-18. You should have done a lot of work on solving these types of differential equations, right? Yes? And so we know that, especially for the first order differential equations, the linear type, we end up with these exponential types of responses a lot. So what does the behavior look like? We start off here with the capacitor charged. And then at t equals 0, the switch flips from green to purple. And the flash flashes and the capacitor discharges. At this point here, we reach the steady state, which is essentially when the capacitor is dead. And so the switch will reset, and that will allow the charging to begin again, and it'll charge until it reaches the steady state value, which will be when Vc equals Vs. Now, and then at this point, right, the flash is ready to go again. T equals tau, both the taus added together. So, the purple, this is the tau discharge. here we have the tau charge. They're different. Okay, and the reason why they're different is because this tau value is dependent on C and the resistance of the bulb. This tau value is dependent on C and the resistance of the source. We can manipulate those values in order to make the taus longer and shorter. There is going to be a trade-off in many regards, in many instances, however. So this is what the answer looks like for this type of problem. Now what we want to do is we want to talk about how to represent it and how to solve it. So how do we represent this system mathematically? We're going to use the same equations that we have from the beginning of this class. We're going to apply KCL for state number 1, which is the purple. And so that is going to be applying KCL at that node right there. One thing to be aware of is that when we're in state 1, none of this over here matters because the green path doesn't exist. So it's an open loop, so it's just non-existent. So when we apply KCL at that node, what we see is that IC plus IRB equals 0. And that's what we have written here. We can also apply Ohm's law and the VI relationship for the capacitor, which allows us to substitute and say C dV dt plus VC over R bulb equals 0. So this is going to be our first order differential equation that we have to solve in order to get the transient. Now, in the next section, we will see that the solution to the equation to the right is VC equals some initial condition e to the negative t over RC. Exponential response, again, like we've seen before. And we're going to talk about how to solve it. We can also define KCL for state 2, which is charging, the charging interval, and then in that case, IC minus IS equals 0. And that is taken from just looking at applying KCL at that node right there. So, the first part of solving any of these transient problems is setting up the KCL or the KVL or whatever expression that we need, setting that up properly, because that's the basis for the rest of the problem. The calculus and the algebra obviously is important, but if you don't start off with a good base, a good foundation, the answer is ultimately going to be wrong. Okay, so moving on to the next section, which is first order differential equations or circuits that are represented by first order differential equations. We ask ourselves, yes?
Can you just roll back up to
Sure.
the state number 2?
No problem. I'll leave them both on the screen. So, is there a general form that we can use for this type of problem? Yes. And this is a form, again, you should have seen in ENG212. The derivative of x with respect to t plus a times the state equals f of t. So the first derivative plus a times the zeroth derivative equals f of t. This is what we're going to call the state, or the independent variable, and this is going to be our externally applied force function. So, right, we should have learned in ENG272 that the solution to this type of problem, first order linear differential equation, can be split into two different parts. So x of t that we're looking for can be split up into a complementary solution to the homogeneous equation. What is the homogeneous equation? The homogeneous equation is when f of t equals 0. Okay? So when we do not consider the external force applied. Then the particular integral solution is also called the forced response. So we have the forced response as well as the natural response. And the reason why these names make sense is because the forced response takes into account the force being applied. The natural response does not take into account that force. And so, for the time being, and this is an assumption you've used in ENG272 as well, we're going to assume that our force function f of t is equal to a constant a. And so what we can do is we can take our solution, which is split into two different parts, and we can generate two different first-order differential equations. One is a function of x sub p. The other one is a function of x sub c. So the particular first-order derivative, zero-order derivative equals a, the external force f of t. Then we have first-order derivative, zeroth-order derivative equals 0, the lack of an external force. And the reason why we can do this, again, goes back to the idea of superposition. Because this is a linear differential equation, we can apply superposition, which means we can find the response in two different pieces and add them together. Additivity. So how are we going to solve these equations? If a is a constant, or f of t is a constant, f of t equals a, which is a constant, then we can assume that the solution x sub p is also a constant. So why does that make sense? So we have dx dt plus a times x equals a. If we plug in a constant for the x's, what's the derivative of a constant with respect to time? 0, so that goes away. And so what we're left with is a times k1 equals big A. And if we move some things around, what we see is that the particular solution is equal to a big A over little a. So this is also equal, this is equal to our x sub p. So that one's easy because of the assumption that we made. Next, what we're going to do is we're going to move on to trying to find the complementary solution. And so in order to do that, we're going to start off by rearranging that expression. So how do we get this form here? Take a look at the homogeneous equation. And you see that what we could do is we could move this whole thing over to the other side, which would give us negative axc, right? And then we could divide by xc. And if we did that, what we would be left with is this form right here, which is the derivative of xc with respect to time divided by that same function equals negative a. And so how do we go from here to here? It uses an identity which has to do with the way that the derivative of a natural log works. So what we see is that when we take the derivative of the natural log of a function, that's equal to 1 over that function times the derivative of that function. Okay? This is something we learned from one of our earlier calculus courses. So what we can do is we can apply this, instead of going left to right, we apply it going right to left. So this form matches this form, and this matches this. So we take this, and we move to that over there. So we end up with the derivative with respect to time of the natural log of the complementary solution equals negative a. And the nice thing about this is it only has xc in one spot, and so we can just solve using integration. So we'll integrate the derivative of a function. What does that give us? If you integrate the derivative of a function, you just get back the function. So we end up with natural log of xc, and then what happens when we take the integral of a constant? It'll just be the constant times whatever the variable is. In this case, it's time. All right, and there'll be constants on both sides that we have to add, a side effect of performing the integration. However, we'll just group them together. And we don't know what their value is anyway, so we could just put the two c's together into another unknown c, constant. So now, lastly, we need to solve this equation. So the nice thing about this is, right, we can simply just say e to the this and e to the that, do that to both sides, and that will get rid of our natural log, because e to the natural log of x is equal to x, right? E and natural log, those are reciprocal functions with respect to one another. So, and that's what this is. The natural exponent, or natural e to the natural log of x sub c, gives us x sub c. And then we do the same thing to the other side. How does this become k2? Well, right, e to the negative a over t plus c is the same as e to the this times e to the c, right? The summed powers, when we apply, well, the identity tells us that they become multiplied by one another, right? E to the a plus b is the same as e to the a times e to the b. So this added constant will become a multiplied constant, e to the c, and since we still don't know what c is, right, so we can just give it another name, k2. We're going to have to eventually come back and figure out what that value is, but at this point, since we don't know what it is, we can just, again, give it another name. All right, so what we're left with is something that looks like this. X sub c of t equals a constant times e to the negative at. And so this is the form that, that we were looking for. And lastly, we can generate the final equation, which what it tells us is that the solution x of t will be equal to the particular solution plus the complementary solution. The particular solution, we got big A over little a, and the complementary solution is k2 e to the negative at. The only thing we don't know at this point is k2. Everything else is a defined constant or parameter of the system or the differential equation that we started off with. Now, if we think about this in physical terms, you'll see that this is the steady state solution. And the reason why that is, look at this component right here. What happens when t gets very large? So e to the negative large number will be 0. So this is going to go away for large numbers, which means that once we settle, we'll only be left with the left-hand component. So this is the steady state solution, and both these together are the transient solution, but this is the predominantly transient component of it, the decaying component of the transient solution. Okay. And then one last thing, I think this is the last thing we'll talk about. Well, we have a couple more minutes. I'll go to 11:30. So what is the time constant? So if I can get both of these in frame here. So for the system above, the time constant is equal to 1 over a. This is the coefficient, or 1 over the coefficient, of t. Right here. So if you look at this form is very similar to this form. We have x of t equals particular solution plus complementary solution. This value, tau, so negative t over tau, the tau is the time constant. So that's how you physically extract it from the math. And in this case, if you compare this to this, we see that tau is equal to 1 over a. And that tau, right, if you go all the way back here, tells us how long it will take for the transient associated with that to settle. Now, I do want to spend some more time talking about the time constant. So what I'm going to do is maybe just tease this, and then we'll really get into it next time. So we keep saying tau is the amount of time that it takes the transient to settle, et cetera, et cetera, et cetera. But an exponential response, right, as far as the math goes, actually never really reaches the value, right? It just gets closer and closer and closer. So when we say it settles, there needs to be some sort of a threshold there that we call settling. And there is. It's mathematically defined and associated with, well, I mean, anyway, so if we have this right here as the total change or the total changing component of the transient, we call it settled, or the difference, so the value of x of t after tau seconds will be 36.8% of what it once was, or 63% settled. Okay, if you think about going from here to here, so it settles like this. This is 100%, this is 50% settled, okay? And so right here, somewhere right here, is the point at which the intersection of tau occurs, when it's about 63% settled, or there's about 36% of the transient left to be settled. Okay, so we'll start with this next time.